Okay, I'm going to pick up with our notes. I'm going to go ahead and just give you the answers since we worked these in class on energy. So if you have not filled in these notes, you can pause the video and fill in the notes that we completed in class. Okay, so the first law of thermodynamics is we also finished in class, law of conservation of energy, or energy in the universe is constant. The total energy is the sum of the potential and kinetic. And while it's difficult to find sometimes the actual initial and final, we can determine the change in energy. We also had worked on this page of notes. So we've got the magnitude, size, and sign of that energy, the energy gained or lost to the surroundings and the sign for that. In chemistry, reactants and products. For our synthesis of water, we had a decrease in our internal energy, an exothermic reaction as we go from reactants to products and create more stable products. For our decomposition of water, we have our final state as the hydrogen and oxygen, which is an increase in that internal energy, and endothermic positive delta E value. So here's where we left off. In most classes in a closed system, we may exchange energy, the system may, by either a heat exchange or a work exchange or a sum of both. The change in energy is heat plus work. So here in this table, if we have a positive heat value, the system would have gained heat. If work is positive, we have a positive work value. Work is done on the system. And a delta E is positive by a net gain of energy by the system from the surroundings. A negative Q is the system losing heat. Work is done by the system, an expansion of gas, while this would have been a contraction of the gas. And a negative delta E is a net loss of energy by the system to the surroundings. So now we're going to apply this to chemical reactions. We've got a piece of dry ice in a cylinder piston arrangement. Okay. So the underlying process is sublimation that allows the gas to expand, turning from a solid to a gas, okay, moving the piston upward. Okay. So the sign for Q has to be positive. So our heat is positive as we go from a solid to a gas. We need to add heat for that to occur. Remember, for your phase changes, these are endothermic and these are exothermic processes. The system absorbs heat. The work is negative because as the gas expands, it does work on the surroundings by the system, expansion of a gas. So here's a mathematical problem. We want to know the energy if we absorb 250 joules, and it does 90 joules of work. So giving it the correct sign, it absorbs. That would be a positive heat value, and it does work. So if it's doing work, it's expanding, so that's a negative sign for work. So a positive sign for heat, a negative sign for work, giving us a total change in energy of positive 160 joules. In a physical change, an endothermic process, heat flows from the surroundings into the system. And in an exothermic process, such as the combustion of gasoline, heat flows from the system to the surroundings. So you've got a beaker of water placed on a hot plate. It's heated, the water boils, the temperature of the water increases as the water changes from a liquid to a gas. In the second scenario, you've got perspiration, produced on our skin while we exercise, and the surface temperature of the skin decreasing as the water goes from a liquid to a gas. Both of these situations involve evaporation of water. And evaporation of water is an endothermic process. It takes energy in to move from that liquid to a gas. Endothermic process. Okay. Explain how situation A resulted in an increase in temperature while situation B resulted in a decrease in temperature. Well, this just depends on what you define the system and the surroundings are. So, if the hot plate is part of the surroundings, which it is, the system is the water. So when you go from surroundings to system, you're going from the hot plate to the water, so you're raising the water temperature. In B, the skin is the surroundings, and the system is the water on the skin. So therefore, heat flows from the surroundings to the system, and you get a decrease in temperature of the skin. So here is the mathematical equation for enthalpy. Enthalpy is energy plus work. So you've got energy, which would have been your Q plus your pressure volume work, E plus PV. I don't think this comes up much in AP chemistry. And of course, the work equation, which we've already used, would go right in here. So when you've got a pressure that's constant in a process, the equation for this work becomes pressure volume work. Most of the processes we deal with are changes in enthalpy at a constant pressure. So we've got heat at a constant pressure. So that's going to give us our delta H term. Okay. Since our pressure volume work is very, very small, since we're at a constant pressure, we're not really expanding or contracting our gases, we've got our enthalpy as delta H. So finally, after all of this, this is where we want to be. Heat energy transferred is delta H. So in terms of a sign of delta H, that's the same as we've always dealt with. So when we're looking at liquid water freezing, that's an exothermic process. Again, when you're looking at phase changes, solid, liquid, gas, you've got endothermic processes, moving particles further away from each other, and exothermic processes. To melt requires energy. To freeze, you have to release it. Exo, endo. So make sure you're clear on your exo-endothermic processes. Enthalpies of reactions, which is where we're headed when we move. All right, so some junior interrupted my video. I'm not sure how I'm going to piece them together, but maybe it just picks up. Let's carry on. The mathematical equation for enthalpy change is the delta H, which is the products minus the reactants. Always products minus reactants. That gives us the thermodynamic sign that we're looking for. So when you see delta H of RXN, that means reaction. Make sure you've got your endo and exothermic signs straight. This is all from last year. So the magnitude is going to be proportional to the amount of reactant that you use up. Okay. And it's going to be equal in magnitude. So the enthalpy change for a reaction is equal in magnitude, but opposite in sign for the delta H of the reverse reaction. So decomposing water versus taking hydrogen and oxygen, making water, that energy is the same, but they have reverse signs. The enthalpy change for a reaction does depend on the state of matter that you are at. So it will make a difference whether you are creating a liquid or a gas or a solid. So when you're looking at the combustion of ethanol to form water and CO2. They tell you that you release 1,235 kilojoules, so your reactants, your products are of lower energy. So it would make a difference whether or not you created water in the gaseous state or it cooled to the liquid state. Aluminum reacting with iron oxide to form aluminum oxide and iron. So this is a typical thermochemical equation that shows you the amount of heat for the reaction as written and the sign of that heat. So using thermochemical equations to calculate heat is just stoichiometry. If you're asked how much heat for a gram of iron, you're going to use your molar mass to form, a gram of iron oxide. You're going to use your molar mass of iron oxide and then just the energy for that equation. So 1 mole of iron oxide releases 848 kilojoules. So if you write it in the delta H form, or you can leave it as this because it says heat released. Same thing here. We can start with heat and figure out how many grams of iron metal we need. So using the molar mass of the iron oxide, we convert to moles of iron and grams of iron. So 848 kilojoules per mole of that reactant. This information was gathered here. There are several ways to do this. You also could have used the energy for the entire reaction and solved it directly from the iron itself. So it says, based on the information in the equation above, determine the value of delta H for these reactions. So if we're looking at this reaction as written, and notice it's making water in the liquid state, okay? If we change the coefficients in front of that, we also change the heat value. Heat does depend on the amount of stuff. So we've doubled our coefficients, we will double our heat, leave the same directional sign. Here we have the same reaction, but we have reversed it, so that will keep the same value and reverse the sign. They ask us the delta H for this, or they tell us that it's not equal to this equation. And that is because we have created water here in the gaseous state, so our reaction must have been at a high enough temperature to hold this in the gas state, okay, versus the liquid. So the total energy value will not be the same. So here's another thermochemical reaction. You write the balanced equation. They tell you how much energy. Okay. So write the thermochemical equation, write a balanced equation, include the states of matter, calculate the heat for this reaction. So you wouldn't know this directly. Okay. So this one is a little tricky. So if you take this reaction, it's got 2 moles of hydrogen peroxide as a reactant. So we're going to go ahead and use the molar mass of hydrogen peroxide and the data that we have in the problem, that 5 grams of hydrogen peroxide release this much heat. That gives us the amount of energy for 2 moles of hydrogen peroxide. Okay? Okay. If we wanted to know the amount of energy for 1 mole, we would have divided that in half. But the equation wants 2 moles of hydrogen peroxide. Down here, if this reaction absorbs that much energy, the reverse releases that much. To make 1 mole of acetylene, okay, so here's your acetylene. To make 3 moles of it requires that much energy, so dividing that by 3, that would be 1 mole's worth. if C6H6 were consumed instead of C6H6 liquid, gas were consumed instead of liquid, would you expect the magnitude of delta H to be less or greater than 630? And actually, you may not be sure why, but it would be less, because if you were already at the gas state, you already had added some energy to get to the gas state, which would be built into this reaction. So since you're already at the gas state, it would be a little less. Okay. Now, calorimetry you should feel pretty comfortable with from the 11th grade. We're looking at changing temperature as energy flows in or out of water, and the thermometer is what we use to gauge that energy flow or that temperature change. We've got specific heat capacity, which we've already defined in previous notes. Our equation, either delta H or Q is equal to MC delta T. They're the same at constant pressure. So if we're doing a simple calculation, and you should be able to do this one even without my notes in front of you, you've got 25 grams of water, specific heat of water. Your change in temperature was 60 degrees, so you'll end up with a unit of joules, which you can convert by dividing by 1,000 to kilojoules if you wish. So here's another calorimetry problem. You've got 5 grams of aluminum, 5 grams of water, both at initial temperature of 25. You bring them together. Okay. Calculate the final temperature for each substance. Well, it tells you that they each absorb, so each sample of matter absorbs that much heat energy. Okay. So you've got 5 grams of your aluminum, okay, at its delta T, and 5 grams of your water at its delta T. So you absolutely have a change in temperature, okay, that's greater, your final temperature of your aluminum versus your water, because of the high specific heat capacity relative to aluminum of water. So here they're summing up that thinking about specific heat capacities and adding the same amount of energy and what kind of temperature you will get. If you have a larger change in temperature, okay, then substance A must have a smaller heat capacity. Anytime you have a larger delta T with the same amount of energy, you have a smaller heat capacity. Here, the same kind of question. You've got magnesium and lead. You add heat slowly. Which substance reaches 50 degrees first? Lead is going to reach 50 degrees first. It has a smaller heat capacity. It takes less energy. It only takes 0.160 joules to raise a gram of lead by a degree Celsius, while it takes 1.02 joules to do the same for magnesium. You've got a piece of copper, and it's sitting in a boiling water bath. You remove it and add it to water at probably room temperature. They give you the... So I had another interruption, so I'll try to pick up from where I left off. I think I was right here where we looked at the change in temperature of the copper in the water, and again, due to their specific heats, the copper has a change in temperature much greater than the water. I want you to look at multiple choice question number 9 and make sure that you understand why B is the best answer, and ask me the next time we meet if you do not. Question number 10 is asking you to solve for the specific heat of copper. So it's based on the idea that you know the heat lost by the copper is gained by the water, so MC delta T of the copper is MC delta T of the water. Setting your two equations equal to each other, because when they reach equilibrium, they will have transferred the same heat. Solving algebraically for specific heat of that copper. So specific heat of copper gives you a value of 0.39 joules per gram degree Celsius. In the next problem, it's a little different. You're asked to find the final temperature of the water. So you can read through and look at the data. You've got a mass of aluminum with its specific heat and an initial temperature, and your mass of water with its specific heat and your initial temperature. What you have to realize is that your metal is going to lose heat energy, so the final temperature is going to be something less than 100, and your water is going to gain that energy, so its final temperature is going to be something greater than the 22 that it starts with. So then you simply go through, collect your terms, do a little algebra, and you come up with the X value, or your final temperature value, of 35.9 degrees Celsius. Again, feel free to ask me if you don't understand how we did this problem. And the last, or next to the last page that we have to deal with is mixing solutions together. So this is very similar to what you'll be doing in lab. The trick to this is making sure that you understand that you need to combine the volumes and then, of course, the masses of those solutions. So my answers are here. There's your balanced equation. So you're free to pause or slow this down so that you can get this in there. Make sure that you understand what I'm doing. So when I've got the 50 grams, that's 25 milliliters and 25 milliliters of solutions that have the same specific heat and density as water, giving us the energy transfer. And of course, this reaction is exothermic. We can see as the temperature increases. Then we're trying to find the number of moles used in this experiment. So now you need the molarity and the volume. To get the number of moles, you need to turn this to liters, but then multiply it by the molarity to get 0.05 moles of HCl. We need that to do the rest of the problem. So they want to know the amount of heat, okay, in kilojoules per mole, okay, for the amount of HCl that we have used. So this is definitely something you'll be doing in your lab in class. So you take your energy and then divide it by the moles, and that gives you 56 kilojoules per mole of heat was released for the amount of HCl that you had. The HCl and the NaOH were in the same molar amount, so that would work for both of them. These questions are pretty straightforward. So our delta T should be lower because heat is proportional to moles. So if we have fewer moles, we have less heat. We actually have half as much heat, looking through that question. The relationship in C would be exactly the same, however, because the amount of heat and the moles are both reduced equally. So that's a really good question. So these are really good conceptual questions based on calorimetry. I'll talk about a bomb calorimeter in class, but I will show you how to work this problem. The only trick to it is that the heat capacity of the calorimeter is included with the specific heat. So let's look at this question. So the delta T is found exactly the same way. And then instead of MC and delta T, the M and the C are combined into one variable that is actually stamped onto the calorimeter. It says 8.2 kilojoules per mole or whatever it can absorb. Those values are the same, and then you just multiply it by the delta T, and then per mole of benzene, turn your benzene to moles, and divide to get your energy transfer per mole. I am not sure I finished. Yep, there it is. So here we've got the energy divided by those moles, giving us 3,280 kilojoules per mole of benzene. So these last couple of questions where you are converting to moles of the stuff, that's really important. Because they want to know, do you understand the difference between the energy for what you found in lab and the energy per gram or mole or whatever it is they ask you here. So this question and the one before that, right in here, those are important concepts. And we'll certainly practice some of those in class. So that should get you up to where you need to be for class the next time we meet.